So we were talking about the compressibility factor. I hope you remember the compressibility factor Z which was written as what? PV by RT. Okay, and this was kind of bar. This was bar, right? So whenever you put a bar on this R, it means you are talking about universal gas constant. Okay, and then if you talk about R without bar, that is basically being represented by R over M, and this M should be what? Come on, this should be molecular weight. So you can say this R bar is the universal gas constant, and when you divide it by corresponding M of any substance, may it be air, nitrogen, water, whatever it is, you would get this R. So please try to distinguish between those things. Okay. And finally, I told you that if you plot this Z with respect to P for any substance, by the way, this graph is for water vapor, I hope so. So you can see how it varies. For different temperature ranges, you can see how does it vary. I mean, it looks very complex to find out a pattern. And I told you that in engineering, we try our best to simplify the things, and we try to find out similarities in the behavior of different materials so that we can have the same relationship for all the materials. So in this case, what did we do last time? We introduced 2 more terms or 3 more terms. I hope you remember reduced pressure and reduced temperature, where we talked about this reduced pressure, where I said you can talk about this P over PC, where PC is what? This is the critical pressure, and critical pressure is corresponding to the point which is being represented by critical point on the PVT surface. Okay, that small point, critical point, the highest point on vapor dome. Similarly, you can define this TR, that is basically T over TC, right? And whenever you define it, try to use the temperature in Kelvin. Remember that. Do not use these things in the other units, right? So use these things in SI units, because they are defined using SI units. Okay. Now there is a point that you should have defined something like reduce specific volume as well. Reduce specific volume, you can define it like this. Okay, but to find out the similarity, we use these 2 terms, and instead of using it, we define a pseudo reduced specific volume. We do not define it like this. A pseudo reduced volume, which is defined as V dash R equals V bar over R bar TC, and you divide, also multiplied with PC, right? So instead of, as far as the compressibility charts are concerned, which we talked about last time, I didn't show you that chart, but now I would show you that chart after some time. But what you can see is, this is V bar, right? This is critical pressure, critical temperature, and this is the universal gas constant, and this is known as pseudo reduced specific volume. Because these terms are defined for simplification of the relationships, that term does not serve that purpose. Okay, using this thing, if you plot Z with respect to VR, simply VR, which is V by VC, you won't be able to get that simplified relationship. Okay. Similarity in the curves for different substances comes in when you talk in terms of pseudo-reduced specific volume. Now, let me show you okay, gentlemen, this is that compressibility chart. Okay. In that chart, you can see that PR is from 0 to 1. PR is from 0 to 1. In the next figures, you may be able to see some other. Here, PR is from 0 to 10. So you would find different figures, I think 3 or 4, 3 figures for different ranges of PR. If you have PR equal to 1, you should go straight away for this chart to find out the corresponding value. How do you see it? We will talk about that later on. But the point is, you should be able to identify that this is your PR, and if you see those solid lines, I am just talking about those solid lines, I hope you would be able to see that. Those solid lines where you can see this 1.05, 1.10, 1.15, 1.20, these are defining what? PR value. So if for any PR value, let's say 0.9, you have got TR equals 1.10. So you would go from here to here. This is the curve for 1.10, and you would see what the value of Z is. It is almost 0.74. I hope you understand that. Okay. So that's how you need to look at those charts. By the way, those charts are used for what kind of substances? Ideal gases. You remember that? Ideal gases. So this is another way of looking at the properties. By the way, what that Z is trying to define, this Z is also trying to define the relationship between PV and T, isn't it? That Z is equal to PV over RT. But the same kind of trend is also looked upon by those property tables. So if you have liquids, if you have gases, you can use those property tables. But if you have ideal gases, you have another way to look at those properties. Right? So these are two different things, basically leading you to the same conclusion. Those two approaches are valid for ideal gases or gases, but the property tables are only valid for what? Liquids plus ideal gases. Okay? Sorry? It is T over Tc. Okay. No, not from the table, by the way. Not from the table. You can't see it from the table. You calculate that, let's say temperature value is given to you. For example, temperature value is given to you, let's say 300 Kelvin. You would see that it is air or it is water. You would find out its critical temperature. You would divide that 300 by that critical temperature in Kelvin. You would see this is its reduced temperature. Okay, then you would be able to find that. Now, in some cases, you may be given the value of Z as far as the numerical problems are concerned. You may be given the value of Z, and you also may be given the value of PR, let's say, and you may be asked to find out TR. So at least two properties should be there to find out the third one. Now, just look at that. These dashed lines, I mean, this is quite tricky. It looks complex, but if you look at it carefully, it would be easier for you. If you look at those dashed lines, 1, 1.10, 1.20, 1.30, those dashed lines are defining this pseudo-reduced specific volume. Pseudo-reduced specific volume. Now, for example, if I ask you that you have a pressure of, let's say, 0.85, a reduced temperature of, let's say, 1, and a pseudo-reduced specific volume of 0.70. So you can straight away go to this one. Right? You can see that at this point you have PR equals 0.85, TR equals 1, and VR equals 0.70. Right? So just see that if you want to fix the pseudo-reduced specific volume, you need to travel along this line. and in that case your TR and your PR would change. Do you understand that? Okay. Yeah, this whole solid line represents the same value of pseudo reduced volume. You can interpolate or you can approximate. Okay. What are these what? You are talking about these dashed lines? Okay, this is the value for what? TR equals 1, TR equals 0.60. And by the way, if you see that those dashed lines are slightly thicker than these one. Okay, still those dashed lines are relevant to those TR values. They may be extrapolated, something like that. It is a way to show that those solid lines are based upon the actual data, maybe, right? So, sorry? Yeah, maybe no. They just have been obtained from the extrapolation or just by the numerical technique. They might be showing something like which is a guessed behavior. Okay. No. It is just ideal gases. PV equals RT is for what? It's the ideal gases. Do you remember that plot where I told you that if you plot this thing against R, you would be led towards one value, which is R bar, and that is only, and by the way, these lines are for different temperatures. Okay. So anyways, this is what it is. That's how it looks like. Okay. So this is for reduced pressure. I mean, few different values are there, and this is PV bar over RT, R bar T, or you can say PV over RT because both the M's would be cancelled down. So you can see that there are points for different. Substances. Okay, and it is just a trend that you can see that it is TR equals 1, TR equals 1.10, TR equals 1.20, and this is from 0 to 7. This is from 0 to 7. Okay, so I mean those charts are there, and those charts have been experimentally that data has been experimentally measured. It has been given to you in the form of charts or in the form of property tables. The only thing you should remember that those property tables are what? Those property tables are applicable to both the liquids and gases, but those compressibility charts are only applicable to ideal gases. Okay, please remember this thing. Please remember this thing. Sorry? You are talking about V bar, okay. You talk about just look at this thing. Specific volume per unit molar mass kind of thing. That is what it is. Right? Okay. Any other thing? So please remember that there is something different in the case of specific volume. That is not the PET reduced specific volume. That is what? Pseudo reduced specific volume. Okay. No, you are not going to use any of these plots. You are going to use these plots, right? And those plots were also part of those property tables which I have sent you. Okay. So, any other thing? And by the way, just you can say just keep your eyes familiar with those kind of tables, because you would be using those kind of charts for not only for this subject but also for thermodynamics 2, for also heat and mass transfer, and then for refrigeration and air conditioning. And if you jump into power plants, yes, you're gonna use those charts there as well. Okay, so right, let's solve this problem. Just to look at the applied side, or how to look at those values. A closed rigid tank filled with water vapor. I mean, by just looking at that small sentence, I can straight away say that its volume is not going to change, isn't it? A rigid tank. I mean, if rigid tank is there, it would solve many problems. So a closed rigid tank filled with water vapor, initially at 20 megapascal, 520 degrees centigrade, is cooled until its temperature reaches 400 degrees centigrade. Now remember that you are going to talk about water vapor, so then you can model it through what? Compressibility chart, because you are going to talk about the gaseous form of water. Okay, so if it is simply water in the liquid form, then you won't be able to use those compressibility charts, right? So using the compressibility chart, determine first one, the specific volume of the water vapor in meter cube per kg at the initial state, the pressure in megapascal at the final state. Okay, so let's try to figure it out. First thing which we can see from this is V remains constant, because M also remains constant, so it means V would also remains. This is the volume, this is mass, so obviously specific volume would also remain the same. Now let's talk about those two states. Initially at 20 megapascal, 520 degrees centigrade, it means T1 is equal to 520 degrees centigrade, P1 is equal to 20 megapascal. Fine. Now, because we are talking about the compressibility chart, and to look at the properties, you have two options. Either you jump onto those property tables which we have already learned, or you can jump onto those compressibility charts. So first of all, if you want to use the compressibility chart, in what terms you need to talk about? Reduced temperature, reduced pressure, reduced pseudo volume, specific volume. So for that matter, we need to find out TC and PC for water. TC and PC for water. Now those values I think those values are given in table A-1. This one. Okay, just see. For water, what is its critical temperature? It is 647.3. Similarly, what is its critical pressure? 220.9. Okay, so this critical pressure is 220.9 bar, and what is its critical temperature? It is 647.3 Kelvin. So convert it into Kelvin. What value would you get? Come on. This is 793 Kelvin. Okay, fine. Or can we convert it into megapascal or kilopascal? Yes, it is 22.09 megapascal. Okay, just divide it by 10 if you want to convert it into megapascal. These unit conversions should be on your fingertips. Remember that. Okay. You guys have made a lot of mistakes in your first quiz as far as those units are concerned, right? So please don't do that. So reduced temperature at state 1 would be equal to what? 793 over 647.3, and you would be able to get 1.23. Similarly, you can get PR1 equals 20 over 22.09, and that you would be able to get 0.91, right? So PR value is there, TR value is there. Can you find out the value of Z? Can you find out the value of Z? Yeah, you can find out that value of Z, and for that purpose we need to go towards that chart. Yeah, this one. What was PR? It was 0.91 somewhere here. What was TR? It was 1.23 somewhere here in between, right? So what would be the value of Z? It would be around 0.83, 0.84, isn't it? It would be around 0.83, 0.84. So I can say that this value of Z is 0.83 or 0.84, whatever you guess, right? So try to be, at this stage of your training, you should be very careful. I mean, do not just see that, okay, fine, it is 0.8, not like that, okay? Just try to pinpoint the value. So this is 0.83. Now similarly, what we need to find out, I'm sorry, we need to find out specific volume at the initial state. So I hope you remember the relationship between P, T, Z and V. How you can relate them? PV by RT equals Z. Fine. So you can say that it is PV by RT equals Z. And what that R is? That is basically R bar over M. Remember that. Do not make that mistake. This R is R bar over M. The values which we talked about last time, that was for R bar. You need to divide it by the molecular weight of water. That is 18.02. I hope you remember, right? Otherwise you can see that from the same table A-1. So you can find out that value of R, and you can find out the value of Z. Obviously you know this P, you know this T, you can find out that V, isn't it? So from here you know this V1. Now straight away from this thing, that V1 would be equal to what? V2. Yeah, sure. But my point is, how would you find out this value of R? If you want to find out that value of R, I'm not going to use V bar over there. Yeah. Either you divide it over there, or if you want to use R bar over there, find out V bar and then divide it by M. So either you have to divide some term by M at the first stage or at the later stage. In any case, you have to do that.
But in this method, you already know that this water, it will remain at thermal state even at 400 degrees. However, if it is not water, we don't know that at 400 degrees centigrade, will it be vapor or liquid?
Use these tables once you have what? You are sure that you are going to talk about the gaseous state. Okay. So V1 equals V2. So what is the next thing which we need to find out? The pressure in megapascal at the final state. So for the final state, we can also see this is P2 V2 over R T2 equals Z. Right? That's how we can find that out. Do we have T2 with us? Yeah, we know T2. That was 400 degrees centigrade. So T2 is equal to 400 degrees centigrade. So what is PR? That is 400 plus 273 divided by what? 647. So find that value of TR. It is 18.02, I think. isn't it 18.02? If you look at that last value in table A-1, just see what that m is. Yeah, I'm talking about the same m. You are talking about that capital M, and that capital M is what? Molecular weight. Okay. So come on, give me that value of TR. Yeah, this was 1.039. So we can approximate it to be 1.04. Fine. So what is V2? V2 was, come on, I have that value equals 0.0152 meter cube per kg. And can I find out the reduced pressure, pseudo reduced value of this one? Can I find that out? So what would be that pseudo reduced value? This would be over R TC. So sorry, this is V by R2. That's how you represent that pseudo reduced specific volume. So for me, that value comes out to be 1.12. You can just plug in those numbers over there and find that out. Now you have pseudo reduced value equals 1.12. You have this TR equals 1.04. Now tell me how you can find out that P2. Come on. You can go to the compressibility chart, fine. So let's go to that chart. Okay, look at those values. Can you guess anything? Stand up. So you want to find out the value of pressure which is there in this chart in terms of reduced pressure. What you can see is you have TR equals 1.04. So obviously this is the line for 1.05. So it should be very close to it. So it may be somewhere here, very close to it. And then you have VR equals 1.12. So you may be having that value somewhere here, where the cursor is. Okay. And what is that value? PR equals almost it's 0.7. Okay. So what you can see is that PR value from that chart is 0.7. So how you can find out P2? PR into, sorry? No, you can't see the exact value. I mean, those charts are there to approximate the things, to give you a better approximation. I mean, you can't draw all the curves for all the temperature, reduced temperature values or the reduced pressure values. They are given for most of the substances, for most of the values, and then you can approximate in between. This is the pseudo reduced volume. That dashed line is for pseudo reduced volume. Just see, this is 1.05. So this point is what? This point is defining TR 1.05 and V dash R equals, no, let him speak. VR equals, which dash line is crossing this point? 0.7, right? So just go along this line and try to find out a point where you have V dash R approximately equal to 1.12 and TR approximately equal to 1.04. So doesn't it go somewhere here or here in between, right? It may be like 0.69. Some of you might be talking about 0.70, but at least you know that it should be somewhere there. Okay. Any other thing? I mean, that's how you can look at those charts, and that's how you can get the value which you desire. Any question about looking at those charts? Any question? Let's talk about the next problem. 1 pound of air in a piston cylinder assembly undergoes a thermodynamic cycle consisting of 3 processes. Okay, fine. Process 1 to 2, constant specific volume. Process 2 to 3, constant temperature expansion. Process 3 to 1, constant pressure compression, right? And some properties are given for different states. At state 1, your temperature is given, it is 540 degree Rankine, and the pressure is 1 atmosphere. At state 2, the pressure is 2 atmosphere. Employing the ideal gas equation of the state, and what is that ideal gas equation? PV equals RT, and what that V is it the larger one or the smaller one? It's the smaller one, remember that, okay? So, employing the ideal gas equation of the state, sketch the cycle on PV coordinates. Sketch the cycle on PV coordinates. By the way, I hope you understand we have how many projections? 3 projections, PV, TV and PT, right? So let's talk about that projection, and that projection would be, if I draw it over there, PV, so those isotherms are going like, isn't it? Do you remember that? So let's say this is the first state. Assume this is the first state. First process is what? Constant specific volume. Where would your state 2 be going? Straight up. Why? Because on those 2 states your volume is. Let's talk about the other thing. Constant temperature expansion. Now it would go along the isotherm. Fine. So it would go along the isotherm, and this may be your state 3. And then finally it is constant pressure compression. So it means it would go from here to here. So this is how you represent your cycle. Do you understand that? Any question? Okay, fine. It is asking about the temperature at state 2. It is asking about the temperature at state 2. So at state 2 you would have P2 T2 over what? Oh, I'm sorry, that was PV over RT. So that could be PV RT, and okay, this is 2, and this would also be 2, right? So come on, tell me, how can you find out T2? Specific volume at state. Okay, as far as that state 1 is concerned, you have P1, you don't have any V1, but you can have R and you can have T1. Can you find out that V1? So that V1 can be used over there. Why? It's a constant specific volume, because state 2 would be at the same specific volume, right? So you can jump onto state 1 V2. So by doing this thing you can find out T2. So can you get anything about the specific volume at state 3? Okay, you tell me, the last man. Yeah. Middleman. So from this thing you just need to see this T2 was equal to T3, right? And then P3 was equal to P1. So just by using that equation you can straight away look at V3. Okay. So what was the equation for that polytropic process? That was PV N equals, and I hope you understood that during this talk we also discussed something about that data fitting and quasi-equilibrium processes, right? Now the point is that if you want to find out work done by a system, you can do that by PdV, isn't it? So if we just talk about some ideal gas, we know that we can say that PV equals RT, and for example if I say that this is N for any liquid or gas, doesn't matter, because this polytropic process is valid for both the liquids and gases, valid for liquids and gases. But this equation is only valid for ideal gas. So if I just look at this equation, can I say that this is P1 V1 raised to power n equals P2 V2 raised to power n, because both of these things would be equal to the same constant? Can I say that? So it means P1 by P2 would be equal to V2 by V1 whole raised to power. Can we say that? Okay, fine. Now if I want to find out work done by during those processes, I can say from state 1 to 2 right. So this thing you can see the solution is given in your example 2-1 in your book. You can see that. Okay. So P2 V2 minus P1 V1 over 1 minus n, and what that n is? That was the exponent of that volume, right? Now if exponent is equal to 1, n is equal to 1, in that case PdV would be equal to P1 V1 natural log of V2 over V1. Okay, I hope you can do this integration. It's a simple thing. Now for ideal gases there are few other relationships. For ideal gases, those relationships are T2 over T1 equals P2 over P1 raised to power n minus 1 over n. I mean, just plug that number into it. Just write down write down what V in terms of T, and you would find that out. Or you can have V1 over V2 raised to power n minus 1. The derivation is very simple. Just plug in the value of V from ideal gas relationship to get this relationship, or plug in the value of P from ideal gas equation to find out this one. Okay. Now if you want to find this work done from state 1 to state 2 in terms of temperature, this one, you are talking about this one. Okay. If you see that this is P1 V1 equals P2 V2, do you have this relationship? But at the same time you have what? PV over RT is equal to 1, right? So can you find out, let's say if it is 1, can I say this thing? So using those two relationships I can go to any one of these, right? It is just the substitution of one value in the form of one variable and the other variable. So in that case you would have MR T2 minus T1 over 1 minus n when you have ideal gas and n is not equal to 1. So remember that this m is the mass. This m is the mass. Similarly, from state 1 to 2 PdV, you would have mRT natural log of V2 over V1, and this relationship is valid for ideal gas and n is equal to 1. Is that quite straightforward? Come on, if you have any question you can ask. Which one? This one? No, n is equal to 1. I mean, this relationship is valid for only this condition. When n is equal to 1, okay, fine, just see. What is that? What is that? This is P1 V1. What is that? So from ideal gas, can you say this thing? Now this is the volume, remember that this is the volume which I have talked in terms of meter cube per kg, so that is why this m is over there, right? So essentially in its true form this is PV equals RT, this is the specific volume. If we convert it into this, it would bring this m on the right hand side. Okay, so I hope you understand that. Any question? Sorry? Here? Okay, tell me, how did I come up to this one? Just think of it. I just plugged in the value of MRT2 over there and MRT1 over there. So MR would be taken as a constant and T2 minus T1 would be there in the bracketed term. Here? Why it should be? I mean, if I just change this one, so it would be simpler, this thing. Let's solve one problem out of it. By the way, I'm not going to solve this problem because I think we have already done with this ideal gas model. Okay, let's talk about this one here, because it is talking about polytropic processes. So let's solve this problem. So it says air undergoes a polytropic compression. So whenever you see a word polytropic, you should straight away think about PV raised to power n equals constant. Okay. In a piston cylinder assembly from P1 equals 1 atmosphere, T1 equals 70 degree Fahrenheit, 2P2 equals 5 atmosphere. I mean, you can see that you can use the relationship for work for n which is not equal to 1, n is equal to 1.3, and I hope you understand the difference between n for a polytropic process, which is the exponent, and n which is there in the ideal gas model, that was number of moles. So then you have work done which was equal to MRT over T2 minus T1 divided by 1 minus n, because you need to find out work per unit mass, so you don't need to worry about mass. Okay, so how to find out that T2 minus T1? You can go back and check this relationship. Okay, this one, T2 minus T1, T2 divided by T1 equals P2 by P1 raised to power n minus 1 over n. So you can find out T2 and you can use the work relationship for finding out work per unit mass. Okay, then what's the next point? Yeah, how to find that out? Come on. Do you know any relationship between work, energy? What is that? That is first law of thermodynamics, right? So that is first law of thermodynamics. So in first law of thermodynamics, what kind of energies were involved on the left hand side? That was kinetic energy, potential energy, and internal energy. So generally we do not talk of the potential energy and internal energy if we are talking about a gas. Okay, generally we talk about those two terms when we deal with something rigid. Okay, so otherwise for gases everything is incorporated into internal energy. So then again m into u2 minus u1, you know that. Now can you, if you have P and if you have T, would you be able to find out anything about U? Come on. How can you find out U, by the way? Yeah, that is CV into delta T. CV into delta T. And you can find out that constant specific heat, specific heat at a constant volume which was used for delta U. You can do that from, you can have that value from the table, which was I think A-1. That CV is also given there. So that's the point in there. You can see that ideal gas model with constant specific heat ratio K. It means you are not going to take CV or K as a function of temperature. You would just take its constant value or averaged value. You won't be worrying about the relationship between CV and T, what would be the value of CV at that constant temperature, or let's say the other one. But what you can do is you can find out the same CV, which is I think there in table A-1 for air. You can use that value. You have T2, you have T1, right? So you can find out what? Delta U. You can find out delta U. And if you add delta U and W, do you remember that relationship? Delta U equals what? U minus W. So if you add delta U plus W, that would be the heat transfer. So from next time onwards, we would start chapter 3, inshallah. Oh, sorry, chapter 4. Okay, thank you.